Okay, I'm going to start. I guess 3 is a quorum. So the first thing is that I put up some notes on the quantum homomorphisms on the webpage. They're a bit rougher than usual, which is probably a scary thought, but anyway, that's what I had, so I put them there. And I haven't had a chance to revise them or anything. So the other point is that I also started the third assignment. Now, I probably won't be closing off questions on the second assignment, but I do expect people to do about an equal number of problems on each assignment. So if you don't do a proper job on the third assignment, then I might take that into account when I work at your grade. So we're going to talk about quantum homomorphisms, but not right now. I need to go back and cover a topic in algebraic graph theory, namely equitable partitions. Okay, so I'm going to give you a definition and some examples, and a little bit of the theory. So we'll be dealing with partitions of the vertex set of a graph. Okay, and I'm going to change the definition a bit before on, but for the moment, the simplest case, we'll say the partition is equitable if each cell of the partition induces a regular graph. Okay, so the subgraph, it's not that each vertex in the cell has got the same number of neighbors, it has the same number of neighbors in the cell, and the edges joining one cell, vertices in one cell to another, form a biregular bipartite graph. So you've got a bipartite graph, the vertices on one side have valency K, the vertices on the other side have valency L. The partition has got this sort of regular structure. And so if that happens, it's called equitable. Now, I will actually eventually refer to this as equitable relative to the adjacency matrix, because there are variations of equitable, but we won't worry about that right now. So this is the sort of the graph theory definition of equitable. It's actually not the easiest one. It's straightforward enough, but there are better ones too. There's a different definition, which is somewhat easy to work with. The other comment is that equitable partitions were introduced by Schwenk in work on spectral graph theory. But whenever people started trying to produce programs to compute automorphism groups of graphs, they had to deal with equitable partitions. And so Brendan McKay, for example, worked out a lot of the theory in the process of putting together the Naughty, which is one of the standard programs for doing graph isomorphism. Now, okay, so I've given you the definition. What's some examples? The one class of examples is given by if you take a graph and you pick some group of automorphisms, not necessarily the full automorphism group, then the orbits of that group form an equitable partition. And I'm not even going to make that an exercise. It's very easy to see. So the orbits. And so this is a messy looking example. This is the Peterson graph. And it's got on 10 vertices, it's got the stabilizer of a point has 3 orbits. In this case, the vertex 0, 1, the 3 neighbors, and then the 6 things distance 2. It's not obvious from the drawing, but the edges I've written in blue there give you a 2 regular graph on 6 vertices, and you can see it's connected, so it must be a 6 cycle. So you have a 6 cycle there, and a co-colligative size 3 there and 1 there. And so that's an example of an orbit partition, and you can see that it's equitable. Each vertex in this cell has exactly 1 neighbor in that cell and exactly 2 in that cell. So the edges joining this cell to this cell give me a bipartite graph with vertices here having valency 2 and the vertices here having valency 1. Any questions at this point? Okay, so it's a little disappointing in terms of the algorithms for graph isomorphism. Your life would be easier if or McKay's life would have been easier if any equitable partition was an orbit partition. And this is a simple example to show that's not true. Okay, so here's a graph, and I've got a partition with 2 cells. I've got 3 and 6, and 1, 2, 4, 5, 7, 8. Now the 1, 2, 4, 5, 7, 8, they induce a subgraph which is 3 copies of K2, so it's a 1 regular subgraph. And 3 and 6 give you a co-colligative size 2. Now each blue vertex has got 3 black neighbors, and each black vertex has got exactly 1 blue neighbor. So this is an equitable partition. But it's not an orbit partition because there's no automorphism. The graph can map this vertex is degree 2 to that vertex is degree 2 because this vertex is on a triangle and that is not. So it's quite easy to find more generally, if you have a strongly regular graph with Schubert automorphism group, which there are large numbers, then the partition with one cell is equitable. The graph's regular, but it's no. So anyway, so all I'm going to say, yeah, getting ourselves distracted. So this is a simple example to show, as I said, that not every equitable partition is an orbit partition. I've also sort of got a diagram to illustrate some of the things going on here. So in this case, I've got two cells, which I'm originally calling C1 and C2. Okay, I should do C2 in blue. Now, each vertex in C1 is adjacent to one other vertex in C1. So we have this, and it's adjacent to one vertex in C2. And each vertex in C2 is adjacent to three things here and not adjacent to anything else. So that picture summarizes the data involved in that partition. And it tells me the valency of each cell and the number of edges joining a vertex in one cell to a vertex in the other. And now I won't be making much use of this. I mean, when you're working with dysregular graphs and things, you spend a lot of time staring at these sorts of diagrams. But the important thing now is simply that being orbit partitions are equitable, but not all equitable partitions are orbits. And well, another example is you take a strongly regular graph, and take any graph, pick a vertex, and you can define the distance partition. You partition the vertices of graph according to the distance from your chosen vertex. So take a strongly regular graph, pick a vertex, and partition by distance. You get a partition with three cells. You have the vertex, the neighbors, and then the things at distance 2. Okay, and so that's a strongly that's an orbit. That is a distance partition, and I'm going to give you the chance to prove that the distance partition with respect to a vertex in a strongly regular graph is always equitable. And that is actually getting fairly close to the definition of a strongly regular graph. You can turn it into one with a little bit of work, but we won't worry about that. So, and so in general, again, this will not be an orbit partition. It is for the Peterson graph, but there are lots of, in a sense, you could say that for most strongly regular graphs, this is not an orbit partition. I don't need to justify that, so I won't. And so so again, I've worked out the orbit partition. What's going on for the Peterson graph again? And I've drawn the picture. So this is partition. There are three cells: C1, C2, and C3. The vertex 1 has got three neighbors in this cell and none in this. So you get this. This is the what I would call the quotient diagram. This summarizes the data, the valencies involved in the partition. Now, for later use, if we're dealing with partitions, and since I want to work with linear algebra, at some point I want to represent my partitions by matrices. Now, I've done this before, but I'll do it explicitly again. So I want to represent each partition by a matrix. Now, a partition is a set whose elements are cells, which is a subset. And so each cell is a subset of the vertices, and so I can represent each cell by the characteristic function of the cell. So the vector, which is 1 on the vertices in that cell and 0 on the others. And so then for each cell, I get a vector of length, number of vertices of the graph. And so I can arrange those vectors as the columns of a number of vertices of the graph times number of the cells of the partition, a matrix, a 0, 1 matrix. And so I've done that in this case. Okay, now I'll probably repeat myself shortly, but the thing to notice here is that the sum of the columns of M is 0, 1's vector. So each vertex of the graph is in some cell. Okay. The other point is that the columns are actually pairwise orthogonal, because they're 0s and 1s, and if you have a 1 in one position, you have a 1 in one position in a column, you have a 0 in the corresponding positions in the other columns. So they're orthogonal. And so when you write, for example, here, a computed M transpose M, you get a diagonal matrix. And that's diagonal because the columns are orthogonal. Now, the entries of that diagonal matrices are the size of the cells. Okay. Now, it turns out sometimes we have an orthogonal basis. Sometimes it's better to be greedy and to scale the columns so that they're unit vectors, and then you have an orthonormal basis. So this is the characteristic matrix of the partition. And if I scale to make the columns unit vectors, then I'd have the normalized characteristic matrix. Okay, and sometimes it's more convenient to work with the normalized matrix. So for the normalized matrix, the transpose times the matrix would be the identity. Any questions? Okay. I was more or less threatening you with other definitions of equitable. So this theorem is giving you the summary. So if I have a graph on n vertices implies a partition of vertices with characteristic matrix M, then the following four statements are equivalent. The partition is equitable. There is a matrix B such that AM is equal to MB. Column space of M is A invariant, and A commutes with this mesh, which is built from M. Now, just to remind you, so this is just our characteristic matrix. This is diagonal. You saw that here. Okay, and this is, so it's trying to be MM transpose, except you've got this diagonal stuff in the middle, messing things up a little bit. Okay, so these things are equivalent. Now, in terms of working and trying to equitable partitions, there's a strong sense in which this is the best definition. The issue is sometimes you want to generalize. You might decide, what if I use a Laplacian? Or what if I'm working with an algebra of matrices? So we want to generalize the definition of equitable to that setting. Then this is the one that generalizes most easily. Okay, this gets to be a mess. So I can define a partition to be equitable relative to a Laplacian if the column space of the characteristic matrix is Laplacian invariant. Okay, now that will have a combinatorial interpretation on properties of the cells, okay, which you can work out. But in a certain sense, you don't need to work that out until you have to. Okay, the requirement is, the important thing is that the column space of an equitable partition is invariant to the matrices that you're playing with. Okay, so let's think a bit about the proof of this. First thing is that these two things, if this equation says that if I apply A to column of M, I get a linear combination of columns of M. Okay, so this equation tells me the column space of M is A invariant. So these two things are easily equivalent. I would say obviously equivalent. Okay, so this is just an explicit form of that. Now, sometimes this is useful, sometimes you want B. Okay, so that's so B and C are equivalent. Now, the other thing this tells us is if you apply A to a column of M, then you get a linear combination of columns of M. But the columns of M are 0, 1 vectors that sum to the once vector. So you're just going to, and so the vector A applied to column of M is constant on the cells of the partition. And that translates into the definition of equitable I gave you earlier. Okay, so that's those two. And so this is the messy one. Well, first thing is, where did this come from? Well, this is a projection. Okay, I'm concerned here with the projection of functions on the vertices to functions that are constant on the cells. Now, the functions that are constant on the cells of pi are a subspace of the functions on the vertices of the graph. And you got the obvious inner product, so you can look for a projection. And I claim this is it, and I'll go through some of that. So I'm going to go through this. So I'm claiming that this guy is a projection. Okay, now the easy thing to see, there's a bit of something missing there, but yeah, the easy thing to see is that this is symmetric. Okay, so that's one condition needed. The other thing is we want it to be idempotent, and so this calculation, when you multiply this times this, you get an M term goes M in the middle, which cancels one of these guys, and so you get that back again. So this is the projection onto the for functions onto the space of functions that are constant on cells. Now, if I'd arranged for M to have orthonormal columns instead of just orthogonal, this would be the identity, and this would just be M transpose. So things would be a little simple in that case, but I haven't done that. So this is rejection. Now we're not quite done, because the point is this matrix, this is M times some matrix. So every column of this matrix is a linear combination of columns of M. So that tells me that this guy is a projection into the column space of M. But I need it to be rejection onto the column space. Okay, and so I need to compute the rank, and I may have made a meal of this, but what I've got works. So using the fact that if I have two matrices A and B, and products A, B, and BA are both defined, then A, B, and BA have the same non-zero eigenvalues with the same multiplicities. Okay, so here's my projection, and I'm going to move. Another typo here. I'm going to move M from the front to the back. Now that changes the matrix, but it doesn't change the number of non-zero eigenvalues or their multiplicities. Okay. Now the point about this matrix, though, is it's just matrix inverse times matrix, so it's the identity. So that tells me all eigenvalues of the non-zero eigenvalues of this are all equal to 1, and it also tells me that the rank of this is equal to the size of pi. And so therefore this matrix represents orthogonal projection. If you've ever had any sort of detailed lecture on least squares, you're trying to solve least squares problems, matrices like this turn up, so that you have to compute them. Now, I should warn you, there's a couple of basic problems I have concerning numerical linear algebra, and one is you never multiply two matrices, and the second is you never compute the inverse of a matrix. So this is the projection, but you don't normally compute the projection explicitly because there's much faster ways of solving the problem. Okay, but you can write down the projection. Once you have the projection, you can write down solutions to least squares problems. So if you have seen least squares done in some detail, you've probably seen this, and that was certainly the first place where I saw it. Okay, so and now that's said. So now I've established this is a projection. But what did I actually want to prove? I say A commutes for that projection. Okay, so this is we'll go through that. Now, there's two parts to this. If P is a projection and A commutes with P, then this says that A applied to a column of P is a linear combination of columns of P. So the column space of P is A invariant. So that's one direction. Okay. So now I'm going to set delta to be the diagonal matrix M transpose M, and what I need to show is that this is my projection. I've just written delta now instead of M transpose M. And so I need to show that these guys commute. And I'm fairly sure there's an easy way of doing it. That's what I did, but this works. So if delta is equal to A transpose M, now we know that AM is equal to MB, so I'm multiplying the left by delta to the minus a half. So if your graph's got vertices of bounces 0, you may want to play a little bit, but we don't want to worry about that. And now all I'm doing here is putting in a delta minus 1/2, delta 1/2 in front of the B. So I get this. So I get that A applied to M delta to the minus 1/2 is M delta to the minus 1/2 times this. Okay, so that would tell me that, for example, the column space of M delta to the minus 1/2 is A invariant, but the column space of M is A invariant, and scaling the columns doesn't change that. But the key thing here is we've now replaced B by this, and my claim is that this is actually a symmetric matrix. Now, I haven't gone into details. This matrix B is in general not symmetric. I haven't written one down here, but if you work it out, this matrix B, when you have AM equals MB, B is in general not symmetric, but it is diagonally similar to, well, as we'll see, to a symmetric matrix. But anyway, we have that. So now what I've just pre-multiplied by this equation, by this, and so I get that this is equal to this. Okay, so in other words, I'll just move the M delta to the minus 1/2 across the front of there. Now, the first thing is that this is symmetric, obviously, and so therefore this is symmetric. Okay, So B itself is not symmetric, but it is diagonally similar to a symmetric matrix. And so this is important. It means it can be diagonalized and the eigenvalues are real and all the rest of it. So B is trying very hard to be symmetric, and you can, with a modest effort, make it symmetric. And now then I go through the calculation. Well, actually, it's worth doing. So this is just my, oops. This is just M transpose M inverted, M transpose. So we have that. And so, but now I've written it, just all I'm doing is splitting the delta into two square roots and rearranging it a little bit. And eventually I get this. I thought I'd said that. Okay. Now the point now is that this is symmetric. Okay. Now A is symmetric, and this is symmetric, and the product of two symmetric matrices is symmetric if only if they commute. Okay, and so that gives me this completes the proof of the last part. Okay. I have a okay. So it took me unreasonably long to work that out. And it's a fact I throw around a lot, so I thought I should prove it in detail once. Okay, so so it's actually important that that we can characterize invariance in terms of commuting with projections, because it turns out as you get into the depths of linear algebra, having questions of when things commute are very important. Okay, and so it's a very useful characterization. And this was something I referred earlier. If A is the matrix algebra, we say pi is equitable relative to A. If the column space of M, the characteristic matrix of pi is A invariant. Okay, so that's the general definition. I mean, it gets more complicated if you look at directed graphs, for example. The first thing happens there is the adjacency matrix is not symmetric, so some of these things will change. And secondly, it's not quite clear whether you want to look at the algebra generated by the adjacency matrix or the algebra generated by the adjacency matrix and its transpose. So in fact, for directed graphs, you've got two versions of equitable, depending on what you want to do. Okay, but there's no commutative involved. You just say, well, in a given situation, it's usually obvious what you're working with. And so anyway, so this is the visual definition of equitable. Okay, so I guess this is what, having done that, this is an implied threat, because now I'm going to talk about homomorphisms, and you won't see any equitable partitions for a while, and you might hope they go away, never come back, but they will. So I wanted to talk about quantum homomorphisms, and I thought I'd warm up a bit by talking about homomorphisms in general. Now, the basic strategy in a certain sense, if we have homomorphisms, there's two important special cases. There's colorings, homomorphisms to complete graphs, and automorphisms. Okay, and we have, in the quantum case, we have quantum homomorphisms, and we have quantum colorings and quantum automorphisms. So so the theories fit together in a very nice way, and there's a lot more going on to make this connection look even stronger. But so but the reason for studying homomorphisms, one reason is that they form a generalization of both colorings and automorphisms. Okay, so it's a natural thing to do, and there's a nice theory. And so for quantum homomorphisms, it maps, and so there's a strong similarity between the theory for classical homomorphisms and the theory of quantum homomorphisms. Okay, and the basic strategy in these things is, okay, so, you first write down the classical thing using matrices, and there'll be 0, 1 matrices. And then to get the quantum version, you replace your zeros and ones by projections. Okay, but you'll see that, so don't worry too much about it. Now, the point I want to make about homomorphisms is that there are actually many useful homomorphisms. I mentioned the colorings. We can, and so, okay, homomorphisms to Km, but we can also have homomorphisms. Now, this is the Knaser graph, so its vertices are the K subsets of an M subset, and two vertices are adjacent if they're disjoint. Now, that's an important graph, and basically because of this reason, that if if you choose, you can choose M and K to minimize the value of M on K. Now, you can actually minimize it, it's not an infimum. So you choose M and K to such that M and K is minimal, and K and K admits homomorphism from X. You get something called the fractional chromatic number. Now that can also be defined in terms of well, linear programming, but this is a simple definition, in some way, simple to state anyway. So by replacing Km by this family of graphs, you go from M coloring to fractional coloring. You also get problems, for example, with you map vertices of graph into the orthogonality graph on the unit sphere. So you say two vertices are adjacent on the unit, two unit vectors are adjacent if they're if they're orthogonal. That gives you a graph, and so you can consider homomorphisms from your general finite graphs into the unit sphere. So in all these cases, I'm thinking about X will be finite, but the target doesn't have to be. Okay, and my point simply is that these things come more than you expect. There's a second thing related to the unit sphere, which is in some sense a generalization. There's two of them. You can take the unit sphere and define X and Y to be adjacent if the inner product of X and Y is less than some constant alpha. Usually alpha will be between, well, it can't be less than -1 by Cauchy starts. So usually alpha would be between 0 and 1. So this gives you something called the vector coloring number, the vector chromatic number. Now the vector chromatic number can be computed in polynomial time using semi-definite programming, and it's closely related to chromatic number. So this is important. There's also a related version where instead of less than or equals, you have equality, and this gives something which is called the strict vector chromatic number. And the strict vector chromatic number of the complement graph is the low bus theta. So my point is there are a bunch of parameters which you come up with in graph theory, and they can be defined in terms of homomorphisms into particular graphs. The graphs will probably be infinite, which is sort of unfortunate, means you have to work a bit harder, but they're there. Okay, so we have these sorts, and you'll see more of this as we go on to the quantum homomorphisms. Okay, so we'll be having more examples of homomorphisms into infinite structures. I've got one more here, which looks a little strange. I'm taking the vertices of my graph to be the permutations in the symmetric group on D letters, and I've declared the two permutations to be adjacent if their difference has no fixed point. So that if you write out the permutation in the sort of just as a row of length D, and then a second permutation row of length D, that there's no column where two entries are the same. And so, and then the homomorphism into Y give you the chromatic number, and this generalizes later on to some quantum stuff. So my point is that there's lots of interesting things you can define in terms of homomorphisms into nice classes of graphs. The standard example is take the complete graphs and you get the chromatic number, but you have other choices. And so once you start thinking about, well, you then see that in some sense the quantum theory really just sort of slots in to the classical theory. You're extending some finite things to infinite things, but in some sense, not that much is changing. Okay, so yeah, so so I guess the point of that simply is there are more classes of questions involving homomorphisms than you might at first think. The ones we'll be focusing on would be coloring sort of morphisms, but we'll have to look at some of the others as we go. So finally, I want to talk about quantum homomorphisms. Now, the way I'm going to approach this is I'm going to start by looking at classical homomorphisms again. So a homomorphism from X to Y is a function from the vertices of X and the vertices of Y. Now, in this, actually we can define this for any, actually I'm just saying this is a function, I'm not making any assumptions at this point. Now, the set of vertices of X that get mapped to a particular vertex, little y and y, is called, I call a fiber of F at Y. Now, the fiber might be empty. I mean, the function doesn't need to be onto. Okay, so, but anyway, we have the fiber. And so the non-empty fibers form a partition of the vertices of X, because F is a function that's defined on all the vertices of X. So the non-empty fibers form a partition. So, so in other words, functions give rise to partitions. Okay, now you see we do, and so we denote this partition by pi sub F. Now, since F is a graph homomorphism, each cell of this partition is a coclique. This is not going to matter too much in the short term, but so the point is we have a function from the vertices of X to vertices of Y. We have a partition and we have a characteristic matrix. Okay, now that characteristic matrix is a 0-1 matrix on the column sum to 1. Now the question is, what do I have to add to those properties? How can I characterize those characteristic matrices, which are characteristic matrices of homomorphisms? Okay, so we'll work that out, and then we'll modify that and produce something which is called a quantum homomorphism. Yeah, so, and this is repeating what I just said, that the characteristic matrix of the partition determines the function. Well, you know, determines in some slightly vague sense. As a 0, 1 matrix throws something to 1, and not every such matrix comes from homomorphism. So now here's the characterization for that. Okay, so the point is we're going to get a characterization of the characteristic matrices on morphisms, and then I'm going to modify my characteristic matrices and say that they determine quantum homomorphisms. Okay. Now there's another way of doing it, which we'll also do, but this is showing how we can, in a certain sense, build up quantum homomorphisms from classical homomorphisms. And okay, leave it at that for the moment. So we're assuming we've got amount from vertex set of X to vertex set of Y, and characteristic matrix of the partition is M. So then the claim is that F is homomorphism if only if the following conditions hold. Okay, so, well, the columns have to sum to 1. I mean, each vertex of X gets mapped to a single vertex of Y. Okay, it's a function. Now, we have to be really careful about this, because when we get to quantum homomorphisms, which I need to discover, we're not dealing with functions anymore, we're dealing with relations, and so the difference matters, but it's a function. The support of a column of M is a co-clique. Okay, because the pre-image of a vertex under homomorphism is a co-clique. And this last one's a little complicated to pass, and so you need a bit of practice to think about for a while. But if two vertices I and J are adjacent in X, and K and L are not adjacent in Y, then this product is 0. Now, clearly the way this came up is somebody worked out the definition of quantum homomorphism and went backwards, but I'm not doing that now. So this is saying that we take an entry in the I row and the entry in the J row, and their product is 0. Now, in particular, in this case, K is not adjacent to itself, and so this implies that if I is adjacent to J, you look at the two rows corresponding to I and J, then you can't have ones in the same column, one each. So there's no column with 2 1s in it. Okay, so basically, our best I can say is go away and think about it. I didn't call into proof. Oops. But so this is a translation of the conditions. Okay, I'm not arguing that it's particularly natural, but it works. Okay. Now, the next thing is you can compose homomorphisms by just just form the composition homomorphisms of functions, and so if the codomain of one is the domain of the next, then you can compose. So what this means is that if you take the setup where you have graphs as your objects and homomorphisms between graphs as your arrows, then there's a category there. Now, there is some stuff about categories in the notes. Now, I don't claim to be an expert in categories, and I'm not going to force you to go through it at all, but I'm going to use the language from time to time, and it gives you a guide as to what you might try and prove, what you might ask. But so the point about the categories is you have the functions between graphs, and you can compose them. Now, the requirements are that the composition should be associative and that there should be an identity map. But we won't worry about that now. So the claim here is if I've got homomorphisms from Y to from Y to X. They have homomorphisms from Y to X and from Z to Y with characteristic matrices MF and MG, then this product is the characteristic matrix of this homomorphism. Now you notice that the order changes, assuming I got this right. It's the sort of thing I do 3 times and So this is just because, well, anyway, so the point then is that the products of the matrices correspond, of these characteristic matrices correspond to the composition of homomorphisms. Okay, so what's happening in a certain sense, you've got graphs and homomorphisms, and then at sort of a lower level, you've got these matrices replacing the homomorphisms. And so the multiplication of the functions is giving multiplications of the matrices. And so you've got a different way of looking at what's going on. You can view a homomorphism, as thinking of a homomorphism that way, or you can think of it in terms of the matrices. And the two things are consistent. That's what this is saying, provided you get the order correct. So now for the highlight, I guess, a quantum homomorphism from X to Y is a matrix with rows indexed by the vertices of X, columns indexed by the vertices of Y, and entries are D by D projections Pij. I got that right. So the condition is that the sum of the projections in a row is the identity. Now, the easiest projections to work with are the one by one projections, which are better known as 0 and 1. Okay, so this is replacing the condition in the characteristic matrix of a homomorphism that the sum of each row is 1. Now we get the sum of each row is the D by D identity. If I is adjacent to J in X and K is not adjacent to L in Y, then this product is 0. So you've got two projections now, their product is 0. Now, if you're dealing with 0 and 1 as your projection, that means that they're not both equal to 1. But if you're dealing with actual projections, then you've got more choices. Okay, but this is the official definition of a quantum homomorphism. I'll give you a slightly different version of it in a moment. It again follows, I said the entries in the same row. Yeah, I'll prove it in a minute. The columns, I can't about the columns just yet. The point is that this condition, the fact that if you have a bunch of projections that sum to the identity, they must be pairwise orthogonal, and I'll be running through the proof of that in a minute. Okay, and the other thing is that I'm going to refer to D as the index of the quantum homomorphism. This is my own notation. I don't know that there's a standard. I've got to call it something, so we call it index. Okay, so the index of the homomorphism is just its order, D by D. Now, another comment I need to make is I've got a matrix. I am thinking of P. There's two ways of looking at P. You can view it as a block matrix, so an n by n matrix with D by D blocks. So it'll be ND by ND. And mostly I don't do that. The second way of viewing it is you can define matrices over any ring. So I'm defining, my matrices are going to be defined over the ring of D by D matrices. So the elements come from the ring of D by D matrices, and so I'll have an n by n matrix. So I'll generally think of when I say my matrix is n by n, it could, if you wrote it out as a block matrix, it could be ND by ND, but I would not be writing it out as a block matrix very often. Okay, and so it's important. I'm thinking I can define matrices over a ring. If you do that, you can still multiply them, add them as usual, because that's what rings are for. Okay, and so when I talk about an n by n, quantum homomorphism, say I've got an n by n matrix or an n by m matrix. You might want to say it's ND by MD. Well, don't say it to me. I'd rather think of it as ND as an n by m matrix. Okay. Now, of course, clearly there's two ways I could think of in terms of block matrices. I can think of the way I just described, and basically I found as I work on this stuff that I prefer the second version. Okay. So we have that's the definition of quantum homomorphism, and the point is that what you're doing is you're taking the classical thing and you're replacing zeros and ones by projections, something to the identity. And there's a strong sense in which that's how you get to quantum physics from classical physics, that you replace zeros and ones by projections. But anyway, that's the version we had. Okay, so we can do it as a generalization. Now I'm going to give another definition, which is really disguised version of this, but it's maybe a bit easier to work with. And the other comment is the quantum homomorphism of index 1 is the classical homomorphism. Okay, so we have that. So this is what I was saying, that we have this classical theory of homomorphisms, and to some extent you can view the quantum homomorphisms as sort of filling in gaps. Okay, now what's the time? Okay. So I want to give a slightly different definition. It'll may look more different, but a different definition of quantum homomorphism. So basically, if I have a homomorphism from a graph on n vertices, quantum homomorphism from a graph on n vertices to a graph on m vertices, I have n rows of length n. And each row consists of projections summing to the identity. And the question is how, in some sense, how the rows interact. Okay, and so for the to do that, I need to talk about measurements in the quantum sense. Now, I defined way back at the start, I think I talked about measurements. I defined them in terms of what physicists call POVMs. You have a set of positive semi-definite matrices that sums to the identity, and every measurement can be represented in that form, although you need to data in some cases if you're worried about the post-measurement states. But so basically a measurement was given by a sum, by a collection of positive semi-definite matrices that sum to the identity. Now we're going to be a bit less general. We're not going to just take positive semi-definite matrices, we're going to take projections. Projections are positive semi-definite, but they're a bit easier to work with. Okay, so I'm going to refer to projective measurement to be a sequence of projections that sum to the identity. And so each row of a quantum homomorphism is a projective measurement. I think sometimes when they talk about projective measurements in physics, they might mean pure states, rank 1 matrices, but I'm not meaning that. Okay, I'll allow them to have arbitrary rank. And so if the state of a quantum system is given by a density d, then the result of the above measurement is that when you do the measurement, the output is an index, one of the indices, 1 through d, and the probability you see the ith output is the inner product of d with pi. Now this is non-negative because these are both positive semi-definite, and the sum over I is d comma the identity, and since d's got trace 1, they sum to 1. So you get a collection of non-negative real numbers summing to 1. So you get a probability density. Okay, so each measurement determines a probability density. Okay, so this is standard physics, which, okay, but for us it's just a definition. So we're saying this is what a projective measurement is. And so the next comment, of course, is that each row of a quantum homomorphism is a projective measurement. Okay, and this will turn out to be useful in a number of ways. Now, this is where we need to do some linear algebra, and let's probably bring to I think I set this up as an assignment question, but I'm going to go through it. So an important property of projective measurements is P1 through Pm are projections and they sum to the identity, then the products of distinct terms is 0. Okay, and so here's a proof. Well, you have the identity, which is equal to n squared. Oh, that's easy, and that's equal to this product. I'm going to make that a little more like a J. So that's equal to this. And so now you multiply it out, and so you get a sum of the squares of the pi's and the sum of the non-diagonal terms. Now, pi squared is equal to pi because that's a projection, and this is equal to I by hypothesis. So this is I plus this mess. Now, so this equation implies that this is sum of mixed terms is 0. Okay, and so therefore the trace of those terms is 0. And as pi and pj are positive semi-definite, if their trace is 0, their product is 0. Now I'm going to prove that too in a second. Okay, actually more generally, if P1 are through Pm projections and their sum is a projection, then they're pairwise orthogonal. There's a couple of ways of doing it. One is just to add, if their sum is equal to Q, you add I minus Q to your set, and now you've got a collection of projections, something to the identity. But this is all that we need. So that if you have projections, they sum to the identity, they're forced to be orthogonal. Now, in a sense, this doesn't matter too much, because if this wasn't true, then our definition of measurement would just require that the projections in the row be pairwise orthogonal. But we don't need to do that. We can have this little argument. Now, I wanted to remind you that, as I said, if the trace of this is equal to 0, then this is equal to 0. Now, if you haven't thought about this for a while, it can cause you some grief. So I've written out a proof here. So if P and Q are positive semi-definite, then by the theory we wrote down, we can write P as a product CC star and Q as a product DD star. Okay, and then the trace of PQ is the trace of this, and then as you've got the trace of the mess of matrices, you just start rotating things, and so I've rotated D star to the front, and I get this, and this just becomes the inner product of C star D with itself. Now, so if the trace of PQ is 0, then this must be 0, and if C star D is 0, then PQ, which is equal to this, must be 0 because that's 0. Okay, now this is going to be, we're going to use this without, I'm going to be using this without any sort of apologies or any explanations. But so the important thing is if I have the sum projections equal to identity, then they're pairwise orthogonal. And if I have two positive semi-definite matrices and the trace of their product is 0, then their product is 0. Okay, so we have these things. What's next? So now as a minor variation, I had a measurement just with an arbitrary index set. In the case that I'm concerned about, the index that would be the vertices of a graph. So, and so this is just saying the measurement on a graph Y. It's a predictive measurement where the indices are the vertices of Y. Okay, so it's a predictive measurement on the graph. Now, each row of a quantum homomorphism from X to Y is a measurement indexed by the vertices of Y. Okay, and this actually it's important in the applications, so the so-called applications of this theory when they're trying to set up protocols for quantum games and things. They're exactly thinking they have a matrix whose rows are measurements on a graph. Okay, so this is the way that these things are used. This is coming from the physicists, not mathematicians. Now, I'm going to say that two measurements on Y are compatible if the corresponding rows give a quantum homomorphism from K2 to Y. So you have to go back and look at that condition with the funny products and things. And so, but that's the definition, so they're compatible. And then this is equivalent to saying two measurements are compatible if the product PIQJ is 0 when I and J are not adjacent. So that, but we have a definition of compatible. We don't have to worry too much about that right this moment. But so then actually this is a good place to stop. We define the measurement graph of Y to be the graph with the measurements on Y as vertices. Now this is an infinite graph. Okay, and two vertices adjacent to the corresponding measurements are compatible. And if the projections are D by D, we're going to denote this graph by curly M, Y comma D. And the theorem is that there's a quantum homomorphism from X to Y, if and only if there's a homomorphism X to this measurement graph. Now, I view this is just almost immediate way we set up our notation and things. It's an immediate consequence. So this then says the question of deciding whether there's a quantum homomorphism from X to Y reduces, probably in quotes, to the question of deciding whether there's a homomorphism from X into that infinite graph. But the other thing which is important and which I've been nagging about is that quantum homomorphisms from X to Y are not functions from the vertices of X to the vertices of Y. Technically, they're relations. Okay, and so we have objects, graphs, and we have arrows, which are quantum homomorphisms, and so we actually have a category, but the arrows don't correspond to functions. Now, there's nothing in categories that say the arrows have to be functions; they can be relations, and that's what they are in this case. So, and so the price you pay is that this graph is infinite. Okay, and trying to decide if there's a homomorphism to some infinite graph is in general not a lot of fun, and it's even worse in this case because you don't have a good feeling for what adjacency means. Okay, nonetheless, we can work with this and we can deduce things from this, and so it's useful. And so we have, so we finally brought ourselves to the measurement graphs. Okay, and we have a quantum homomorphism X to Y if there's a measurement graph, and the quantum homomorphism is given by an n by m matrix, each row of which is a measurement. And that's where I'll stop.